So hello, everyone. I'm Professor Anderson Rocha, and I welcome everyone to this section today. We have the pleasure to have today with us Dr. Michael Bronstein. He is a DeepMind professor of artificial intelligence at the University of Oxford and head of graph learning research at Twitter. He is the recipient of the Royal Society Wolfson Research Merit Award, Royal Academy of Engineering Silver Medal, Google Faculty Research Awards, and Amazon AWS ML Research Awards. He's also a fellow of different institutions like IEEE, IAPR, BCS, and ALICE, and also an ACM Distinguished Speaker. And he is a young scientist for the World Economic Forum as well. In addition to his academic career, Michael is a serial entrepreneur, founder of some interesting startups like Novafora, Envision, which was acquired by 2012 by Intel, Video Sites, and Fabula AI, which I believe is the latest one, acquired by Twitter in 2019. This talk today is part of our collaboration of the Institute of Computing here in the University of Campinas, Brazil, and the Catholic University of Rio de Janeiro in the what we called Conexão Rio Campinas, Campinas Rio Connection, an event that brings together researchers to discuss science and especially artificial intelligence and computer science. So Michael, thank you very much for accepting the invitation. Typically we have like 45, 50 minutes for a presentation and then some minutes for question. It's up to you, you control the time. And once again, thank you very much. The stage is all yours.
Thank you. I hope you can hear me well and see my slides. So thanks Anderson for the introduction and the invitation. I would like to talk today about graph neural networks and some recent works that we've been doing in these domains. So this is collaboration with multiple people, including at the University of Oxford, at Twitter, and at Cambridge. So before we talk about graph neural networks and dive into these maybe somewhat more abstract and more exotic topics such as differential geometry and algebraic topology, let me give you a slightly broader perspective. And I would like to open with these two quotes. The first one is from Hermann Weyl. He was a mathematical physicist, one of the most important of the 20th century. And he wrote about symmetry as follows, that symmetry, as wide or as narrow as you may define in its meaning, is one idea by which man through ages has tried to comprehend and create order, beauty, and perfection. So it sounds a little bit poetic, but he really applied this notion to the formulation of modern physics as we understand it. And this is probably best and laconically captured by Philip Anderson, a physicist and Nobel laureate, who said that it's only slightly overstating to say that physics is the study of symmetry. Now, this is the idea that we try to bring to machine learning, so it's not new at all. It has been around in geometry for at least 150 years. And what happened in geometry is that for over 2,000 years, we lived in the world of Euclidean geometry. That was really the only geometry that was known. It was an axiomatic construction built on so-called postulates, where the fifth postulate was a kind of different from the others, and many illustrious mathematicians broke their teeth trying to prove it. And in the beginning of the 19th century, suddenly came the realization that you can actually not prove it. So you can drop it and replace it with some other assumptions, and it gave rise to what was called non-Euclidean geometries. And very soon, this world of geometry basically diverged into different models. It was not clear how they're related to each other, things like elliptic geometry, hyperbolic geometry, projective geometry. And there came Felix Klein. He was a young and fresh professor appointed at the University of Erlangen, and asked to deliver an inaugural keynote talk, a research prospectus, and which he delivered actually on a different topic, but he published his research program that entered the history of mathematics as the Erlangen program, and there he suggested to treat geometry as the study of invariant properties or symmetries of an object. So you essentially you take a space, attach to it a group of transformations, and you ask what kind of properties are preserved by this transformation. And this immediately provided clarity and hierarchy of different geometries. And it also had a cultural impact, not only on geometry and mathematics in general. So follow-up fields such as category theory emerged out of this mindset. But it also made a very important impact in physics, where it was possible to derive, for example, conservation laws from first principles of symmetry and invariance. So this is a remarkable result known as Noether's theorem. And overall modern physics, through the notion of gauge invariance, can be totally derived from considerations of symmetry. So that's why Anderson's quote is so appropriate. Now, in machine learning, the idea of approaching the problems geometrically has also been around for quite a while. And if you think of supervised learning as a kind of function estimation problem, so we are given some complicated function that, let's say, that maps us from the input space of cat and dog images to the binary labels, we can sample at a few points on the training set, right? And we try to interpolate or extrapolate these points on examples that we have never seen before. And what happens is that because most of our input lives in high dimension, then the standard notion of regularity that you can use from approximation theory doesn't work. So it doesn't scale well with dimension, a phenomenon that is known as the curse of dimensionality. And the idea to use geometric viewpoint on machine learning problems the idea to look at these problems geometrically was already there in the 60s. So as you probably know, some of the standard way of representing these functions is using neural networks such as perceptron introduced by Rosenblatt in the 50s. And the book Perceptrons by Minsky and Paper that criticized these architectures actually used results from group theory to show what kind of functions these architectures could not represent. But I think it's fair to say that the kind of organizing power of group theory and invariance and symmetry in machine learning has not been recognized until recently. And that's what we are trying to do in a framework that we call geometric deep learning. So we try to think of our data as coming from some geometric domain on which we can define a symmetry group, and its action on signals that live on this domain can be incorporated into machine learning architectures, into functions that take as inputs these signals in the form of invariance. And the classical example are convolutional neural networks, where the domain is a plane or a grid. The group is the group of translations, and then it acts as a shift operator on images that live on the grid, and then convolutions are shift equivariant functions. And you can basically derive from first principles one of these classical architectures that dates back to the works of Fukushima and Yann LeCun. Another more recent example are graph neural networks. So in this case, the input, the structure of the domain is a graph. And in a graph, because we don't have canonical order of the nodes, the symmetry that we need to assume is the permutation group. And it acts on the nodes through the permutation matrix, and the typical functions that are implemented in graph neural networks that are equivariant with respect to this symmetry are message passing. And more recently, there is a new trend, a new type of architecture that are called equivariant graph neural networks that also account for the transformations of the data at the nodes themselves. And in particular, this is now very popular in applications in chemistry and molecular graphs, where you have both the structural formula of the chemical compound, right? So the graph represents how nodes that represent atoms are connected, as well as three-dimensional coordinates of these nodes, on which you can apply continuous transformations, such as rotations and translations. And because you don't have a canonical orientation of molecule in space, you want to be equivariant with respect to these transformations. So these architectures, probably the best manifestation is the AlphaFold 2 architecture by DeepMind that predicts the folding structure of proteins. Now, this is a very general blueprint. We can apply it to grid structures data, to meshes, to graphs. And one thing that you notice in these examples is, for example, we can think of grids as discretizations of continuous objects, of planes. And we can think of meshes as discretizations of surfaces or manifolds, we don't have an immediate continuous analogy for graphs. And this is something that I personally find disturbing, and we would like to build a model that looks at graphs as continuous objects. And why we need it, basically, if you look at graphs and compare them to meshes or to grids, they have the least structure, right? So if I look at a node and its neighbors in a grid, we don't have any ambiguity, so I can number the neighbors in a particular order that is always the same, right? I can talk about, for example, a neighbor that is to the left of me or to the right of me. On the mesh, I have slight ambiguity, so I still can order the nodes in a certain way, right? So I can order them, for example, in clockwise orientation, but I have ambiguity in choosing the first neighbor. So I have a rotation ambiguity. And in the graph, the ambiguity is a complete permutation of the nodes, because usually, unless I assume some extra structure, I don't have any particular ordering. So graphs have least structure, and basically what we will try to do is we try to endow graphs with some extra structure by, so to say, lifting them into other spaces or into other objects where the structure is, there is more structure and where we can learn and basically bring these results back to the graph. So looking specifically at graph neural networks and how graph neural networks are typically implemented, we operate on every node. So we have some shared function that operates on the neighbors of every node. So basically it looks at the collection of features in the neighbors of a node that I denote here by red. And because we don't have a canonical ordering of the neighbors, this operation must be permutation invariant. Now, if I apply it at every node of the graph, I get a node-wise output, and this node-wise output is easy to show that it will be permutation equivariant function. And you can show that if this function that I denote by phi, this aggregator, is chosen in a particular way, in particular it's injective, then this kind of operation becomes equivalent to a classical result in graph theory that is called the Weisfeiler-Lehman graph isomorphism test. So it's an iterative algorithm that tries to refine the colors of a graph. So it starts with a graph where every node is colored in the same color. And the refinement works in the following way. It looks at the structure of the neighborhood of every node. So initially we have two types of nodes. We have a blue node with 2 blue neighbors and a blue node with 3 blue neighbors. And because of injectivity, these neighborhoods will be assigned a different color. And I can repeat this process several times until the colors stop changing, at which point I can output the distribution of colors and say that this is my kind of graph descriptor. And if I provide you a different graph with a different structure that is not isomorphic to the first one, and I see that the colors are different, I can say for sure that the graphs are not isomorphic. But if the colors are the same, we don't know. So it's a necessary but insufficient condition. And in fact, there are examples of non-isomorphic graphs that would be deemed equivalent by this color refinement algorithm. Now, this is also clear why it happens, and an analogy for this algorithm is imagine that you're given a maze and you don't have a map. So you want, by walking in the maze, to discover its structure. And this is how this kind of walk will look like. So you see that for nodes that appear in different structures, this walk will look the same, right? So these are rooted trees produced by the Weisfeiler-Lehman algorithm. So these nodes will be indistinguishable, and as a result, we cannot distinguish between these two graphs, even though they are not isomorphic. So the standard approach that is taken in the field towards designing more expressive graph neural networks can go in several ways. So one of them is using higher order tests. So basically, it's not a single test; it's a hierarchy of tests that are strictly more powerful. You can use a collection of subgraphs extracted by some policy, so this way you break these regularities that confuse the Weisfeiler-Lehman algorithm, or use what we call topological message passing, where you lift a graph into a more complex structure, cellular or simplicial complex, and there you can do message passing that is probably more expressive. But by far the most common choice is to use what is called positional or structural encoding. So in positional structural encoding, what you do is you attach some additional information to the nodes of the graph, and this way you're able to disambiguate these situations that before that were indistinguishable, And one standard technique that we devised with our students was counting substructures that Weisfeiler-Lehman algorithm cannot detect, for example, triangles, cycles, and so on. Now, there are many other techniques. You can take, for example, the eigenvectors of the graph Laplacian, or use even random features. But I think it's fair to say that there is no canonical positional encoding. So for different applications, there are different choices that lead to different results. So we'd like also to provide some principled approach to the choice of the positional encoding. And the last problem that I would like to mention in relation to graph neural networks is the problem of oversquashing and bottlenecks. And it arises in situations when my problem requires to bring information from distant nodes that are not immediate neighbors, but maybe neighbors that are a few hops away. And the structure of the graph is such that the number of such neighbors is very large. So we are talking about volume growth that is exponential with the radius. And in this case, basically, I happen to have a situation where I have a lot of data that I need to squeeze into a single feature vector. And this is problematic. Basically, it means that the message passing, the propagation of information on the graph is not efficient, and we have a phenomenon that is called oversquashing. Now, empirically, it was shown that oversquashing can be mitigated by decoupling the graph that is used, that is given as an input, from the graph that is used to propagate information. And again, there are multiple techniques that can be employed. And in fact, de facto, most of modern graph neural networks do it in some form, whether in the form of some dropout or neighborhood sampling, or using bigger multi-hop filters, or maybe explicitly doing some pre-computation, rewiring the graph, and then making it better for propagation. But again, there is no canonical way of rewiring this graph. So we would like to give maybe again a more principled understanding of which graph is good and how to change it to improve the propagation of information. Okay, so these will be the kind of three motivating questions. And the approach that we would like to take will be motivated by physics. And what you see here is a figure from a recent paper in Nature, where real-world physical systems, whether optical or mechanical or electronic, were incorporated into deep learning pipeline, and you can backpropagate through them. So this is just a metaphor for us. We would like to think of a system or a process that has underlying differential equations that we can discretize in our domain, for example, on a graph, and which have some control parameters. So think of an airplane that takes off and flies and lands at some point. It has some set of parameters, right? So some control surfaces that can change in order to bring it from one point to another. So we can use terminology from control theory, for example, to talk about expressive power of such models as the possibility of reaching a certain state, right? So the state will be the output of our neural network, and we can talk about reachability, right? Whether certain solution can be reached. We can talk about efficiency, for example, how fast we can get to this point. We can talk about generalization as some form of sensitivity to the initial conditions, and so on. So again, it's a metaphor, and there are multiple physical processes that we can design on graphs, and the first of them will be diffusion. So this is a line of works that was published at Europe's and ICML last year with my collaborators from Twitter and Cambridge. And diffusion is really some of the probably physical processes that have been studied mathematically among the earliest ones. And the first rigorous treatment of this process was by Newton himself, published anonymously in 1701 in Transactions of the Royal Society. And there he describes an experiment and a mathematical model that tries to analyze it, what is nowadays known as the Newton law of cooling, that tells us that the temperature of a hot body, that the hot body loses in a given time, is proportional to the difference between the temperature of the object and the environment. So it's a kind of global rule that tells you that the temperature will change exponentially. Now, it took another 100 years until this law was coded properly in using the terminology of differential calculus that already existed by that time. So this is the Fourier heat conduction law that tells that the heat flux that results from thermal conduction is proportional to the magnitude of the temperature gradient and opposite to it in sign, as written here. And this is his celebrated treatise on the analytic theory of heat, where also the Fourier series appears for the first time. So the final bit that we need is some conservation law, and this is typically known the law of diffusion of Fick, named after a German physicist, that tells us that the temperature change in time equals the heat flux through volume. So combined together, this is the classical diffusion equation that you probably study in an introduction course on partial differential equations. So we have some stuff distributed on a domain, let's say temperature. The difference, right, the gradient of this temperature or whatever quantity creates a flux from point of, let's say, higher temperature to the point of low temperature. And the conservation law tells us that no heat is created or disappeared. So the only change of the temperature is due to the flux through infinitesimal volume that is captured by the divergence, and together this gives us the diffusion equation that is written here. So it's a partial differential equation, temporal derivative on the left-hand side, spatial derivative of second order on the right-hand side. And this diffusion equation can take different forms depending on our assumptions on how our domain looks like, right? The conductivity properties of the medium. So if the conductivity is fixed everywhere, we're talking about homogeneous and isotropic diffusion, and we can show that this process is a gradient flow, so it minimizes an energy, a functional that measures the smoothness of the signal, right? So as diffusion goes, things become smoother and smoother. And actually, in the Euclidean case, you can express it in closed form as a convolution with a Gaussian filter of increasing bandwidth. So we are talking about something that in the limit will smooth everything to constant or an harmonic signal. But what is more interesting is actually diffusion where the diffusivity properties are position dependent, what is called non-homogeneous diffusion, or also direction dependent, what is called an isotropic diffusion. And these kind of diffusion equations attracted a lot of attention in image processing, starting from the seminal work of Pietro Peronna and Jitendra Malik in 1990, where they considered the problem of image denoising, where you try to average out the noise from an image, but if you convolve it with a standard Gaussian filter, then you will, of course, you will average out the noise, but you will also remove the discontinuities that are important for visual perception. So the idea was to make controllable diffusivity that inversely depends on the norm of the gradient, that is indicative of a discontinuity on an image. And in other words, the diffusion will, when it reaches this discontinuity or edge, in the intensity of the pixels, it will stop or slow down. And this is how the kernel of this diffusion looks like. So it's nonlinear, it's position dependent, and comes through this diffusivity function. And here is the effect of what it does to an image. So you see that in the middle, you see the face of Sir Isaac diffused with standard linear diffusion, convolution with Gaussian. And on the right, you see the effect of this nonlinear position-dependent diffusion. So it removes the noise at the same time preserving the perceptually important features in the image. And as a concept, it was extremely appealing. So it gave rise to a class of variational and PD-based methods in image processing and computer vision. And I think it's very elegant because you say that I have some energy, some functional that tells me how my image should look like. And then I derive its optimality conditions, what is called Euler-Lagrange equations, and I evolve my image by gradient flow towards the minimum of this energy. Now, the reason why these methods almost disappeared now from this field with the advent of deep learning is the same reason why other methods disappeared, that it's very difficult to design by hand some functional that would fit well all possible examples of data in all possible situations. And this is what we are trying to do. So we are trying to revive some of these ideas to adapt them to non-Euclidean setting, to graphs in particular, and also to the modern tools of machine learning. So you will see that many of the ideas that are maybe rediscovered in the field of deep learning actually have roots and trace back to these works in image processing. Actually, my PhD advisor, Ron Kimmel, was one of the pioneers and key figures in this field. So for me, many of the things that we see in deep learning nowadays look almost like deja vu sometimes. Okay, so now we move to graphs, and basically what I described before can almost one-to-one be applied to graphs. So we can define a notion of differential operators. Right now, these are discrete operators that we can build on a graph. So here is a gradient. I can define it as the difference between endpoints of an edge. So it takes a signal that is defined on the nodes of the graph and produces a signal that is defined on the edges. Divergence is an adjoint operator, so it does the opposite. It takes a signal on the edges and produces a signal on the nodes. And we can also define the Laplacian, so it's an important operator that you can interpret as the difference between the average of the features in the neighborhood with respect to the feature of the node itself. And with this, we can define a graph version of the diffusion equation that structurally is very similar to what we've seen before. So we have the gradient of the temperature or whatever quantity of features of the nodes. We have the diffusivity function that we can assume to be normalized to 1. And we have the divergence. And this is now the time is continuous here, so the domain is discrete, so it's already discretized. So technically speaking, it's not a PDE, it's a system of coupled ordinary differential equations. And because of nonlinearity, we need to solve it numerically. And the easiest way of solving it numerically is just replacing the continuous time with a fixed time step, and we get what is called explicit or forward Euler scheme. So the basically the k plus first iterate depends on the previous kth iterate through this matrix valued function that looks like this. So in other words, the update, the next iteration, is obtained by linear combination of the previous node features by coefficients that non-linearly depend on the previous features. And this matrix has the same structure of the adjacency of the graph. And you can show that this scheme is stable if the step size is sufficiently small. Now, what is interesting also is that it is equivalent to a class of architectures that are called graph attention networks for a particular choice of the step size and this nonlinearity. And basically, you can interpret multiple types of graph neural networks as special cases or special discretization or special ways of solving this diffusion equation on the graph. Now, we can use other schemes such as semi-implicit scheme. In this case, we need to solve a linear system in order to obtain the next iterate. With the advantage is this scheme is now unconditionally stable, so we can take bigger step sizes. And overall, there is a plethora of different methods in the literature in numerical analysis that allow us to solve different types of such equations numerically. Now, how do we use it for machine learning? So essentially, the idea here is that we parameterize this diffusion equation by parameterizing the diffusivity function. So basically, you start with some initial features on the graph, and let's say the task is node classification. We diffuse this information by some parametric diffusion process, again parameterized by the parameterizing the diffusivity function, and then we run this diffusion, we solve it numerically for a certain time, and then we read out the solution, and this will be the output of our neural network. And by tuning the knobs of the diffusivity function, we can achieve what our task requires, right? So that's where the learning comes. And it's interesting that also many of these equations have associated energy functional. So essentially, we parameterize the energy and not the layers as one would do in graph neural networks, right? So here the iterations of the solver correspond to the layers. And in particular, we have shared parameters across layers, right? Because the parameters of the diffusivity function are time independent, right? So you can ask why to do at all this exercise. So first of all, it gives a completely new perspective on standard problems in graph neural networks. It allows, for example, to interpret existing graph neural networks, such as graph attention networks, as discretized graph diffusion equations. It allows potentially to make educated architectural choices as to, for example, whether you have a residual connection, right, that may correspond to some forms of implicit schemes. You can use maybe some other fancier solvers, such as multi-step or adaptive or multi-grid solver. You can interpret implicit schemes as multi-hop filters and so on. So there is a bunch of interesting things that are probably now not yet explored in the graph learning literature. We also have theoretical guarantees that come from the theory of partial differential equations, such as stability and convergence. And we can also interpret graph neural networks, for example, if we can associate an energy and think of our differential equation as its gradient flow. So we can say that graph neural network minimizes certain functional. And of course, there are deeper links to other fields that are probably less known in graph neural network literature, such as differential geometry and algebraic topology, and this is what I will describe later. So let me skip it. Well, obviously, we cannot publish in EURIPS nowadays or CML without beating some benchmark like OGB in this case by a fraction of percent. So here at the time of publication, we're state of the art. What is interesting, also requiring significantly less parameters than competitive models. Now, in everything that I have described so far, we didn't really have a continuous model for the graph. So we have continuous model for time, right, that replaces layers of the neural network, but the graph is still discrete. And if I take you back again to my example of two-dimensional diffusion in the plane and image processing, so if we discretize our plane, our image as a grid, we have many ways of discretizing our second-order differential operations, like the Laplacian. So here are three ways of discretizing the Laplacian, right? So we can use the standard way, right? The most common, where we use top, bottom, left, and right neighbors. We can rotate the stencil by 45 degrees. We can use more distant neighbors, and because operators are linear, any convex combination of these discretizations will also be a very discretization. So we want something similar for our graphs. So we want to think of our graph as a kind of auxiliary construction, some kind of numerical convenience that we can change throughout our discretization, or can choose maybe a priori something that works better for us. So we want to remove this kind of sacrosanct meaning of the graph and replace it with, so decouple the input graph from the computational graph. And for this purpose, let me describe another framework. So that was our new paper last year that takes a non-Euclidean approach to diffusion. And this is again inspired by works that have been done almost 3 decades ago in image processing and computer vision. So I remind you that the Perron and Malik diffusion had this nonlinear diffusion equation that had position-dependent diffusivity function. An alternative approach is to look at non-Euclidean diffusion. So in this case, we think of our image as a manifold, two-dimensional manifold or a surface that is embedded in a joint space that contains both positional coordinates, so the XY coordinates of the pixel, and the feature coordinates, in this case, the intensity, the R, G, and V channels of the image. And by virtue of this embedding, we can define a canonical kind of metric through the pullback mechanism on this manifold, right? So this is the Riemannian metric. In this case, it's a 2x2 matrix. And with respect to this metric, we can define a non-Euclidean analogy of the Laplacian, what is called the Laplace-Beltrami operator. And the diffusion equation with this operator that is called Beltrami flow is the gradient flow of a generalization of the Dirichlet energy that is called the harmonic energy in differential geometry, or Polyakov functional, or Polyakov energy in physics. So it appears in string theory, and basically you can think of it as a generalization of the previous scheme, where by virtue of the embedding we create this behavior that basically the diffusion kernel now accounts for the distance not only in space but also in the features. So applying this idea to graphs, now every node of the graph is equipped with a pair of coordinates. So the component that I denote here by U, which is the positional coordinate, and component that I denote by X, which is the standard feature coordinate. And now we apply our evolution equation to both coordinates, and the evolution of the U component amounts to the changing of the graph, whereas the evolution of the feature component is the feature diffusion that we've seen before. And the graph rewiring is maybe a little bit subtle point. So you can always find the representation of the graph in some space, but it's usually only an approximate representation. So there are usually no isometric embeddings of graphs into spaces with fixed geometry. So think of it as a kind of auxiliary construction, right? So I have my representation of the graph, and if during this evolution two nodes become closer, I might decide that it makes sense to introduce an edge there in order to facilitate the flow of information between these nodes. And I know that it might sound a little bit cumbersome, so here is a picture that shows, I think, it in a much better way. So what you see here is the Cora graph. So this is one of the standard toy examples that is used to test graph neural networks. So it's a citation network. The color of the nodes here represent some low-dimensional projection of the features. The position of the nodes represent, again, two-dimensional positional encoding. And you see that we are diffusing both, so the colors are changing, the positions are changing. The task here is node-wise classification, so you see that we obtain very nice clusters. And you see that also the graph is rewired on the fly as the nodes diffuse, right, and drift apart. Then we can cut or introduce new edges in this graph, or in other words, perform graph rewiring. So, and this view where our graph changes under our feet, weird and very untraditional for people working in machine learning or in signal processing, but it's very common and very natural concept in differential geometry. So in differential geometry, it's very common to talk about the evolution equations of a domain of a manifold, where you can apply a differential. Yeah.
I think that something that you did with the slides, it's like completely black and your voice is speaking now. Oh, now it's okay. It's white again. For some reason, it was black.
Yeah, maybe some network. Yeah, sorry. So I hope you can hear me. You can hear me again. So basically, what I was saying is that this viewpoint where we have a domain that is changing our feet might be very strange and very unnatural for people coming from machine learning and signal processing background. But in differential geometry, it's very common to do it. And for example, you can apply a differential equation that evolves the Riemannian metric of a manifold in time. And probably by far the most famous examples of such evolution equations are Ricci flows, which look a little bit like the diffusion equation. So you have the temporal derivative of the metric tensor on the left-hand side and the Ricci curvature tensor, which is second order quantity, a little bit similar to the Laplacian, on the right. And Ricci flows were introduced by Richard Hamilton in an attempt to prove the Poincare conjecture. And what the Ricci flow does to a manifold is, you see here, that looks like this dumbbell. If you flow it backwards in time, in this case, it will look more like a sphere and then collapse into a point. So this is how we can characterize topological spheres. So if you take a two-dimensional sphere and draw a one-dimensional sphere on it, right, a closed curve, then no matter how this initial curve looks like, you can collapse into a point. This is what Ricci flow does. On the torus, for example, if I have a curve across the donut, I cannot do it. So the conjecture was that you can do it also in higher dimensions, and it turned out to be difficult to prove in three dimensions. And this is the celebrated result of Perelman that used Ricci flows to prove actually a slightly more general result than the Poincare conjecture. And you may wonder, what does it all have to do with graphs? So what we can do, how we can relate Ricci flows to graphs, is to look at the problem that I mentioned before of oversquashing and bottlenecks. So I remind you that oversquashing is this failure of message passing to propagate information efficiently on the graph due to some unlucky situations where the structure of the graph has bottlenecks, some characteristics that are unfriendly for message passing. So what we'll try to do is to define oversquashing as some kind of sensitivity analysis, and then relate it to geometric properties of the graph that can be expressed through curvature. And then we can use a process that is a little bit similar, inspired by the Ricci flow, to rewire the graph to modify it in such a way that will make it friendlier for message passing, and improve as a result the performance of graph learning. So let me start with the first thing. So what is oversquashing? Essentially, it is some form of insensitivity. So if I have a multi-layer graph neural network, that outputs the features of some node I can look at how this output depends on the input at some distant node that I denote by S. Okay, and under assumptions that there is some smoothness of the activation function, so the Lipschitz continuous, we can bound the derivative of the output with respect to the input. So this is Jacobian. And you see that the bound, well, obviously it contains the Lipschitz constants, but it also contains the structure of the graph through the power of the adjacency matrix that I denote here by A. But it's not very clear here how the structure exactly comes across, right? Well, some power of A, it's not very explicit, but intuitively we understand that some graphs might be worse than others. So for example, we are probably not expecting to see this phenomenon to be very dramatic in grids, but we expect it to be very dramatic in trees, which is actually a pathological case, right? So there, depending on the depth, we get exponential decay of this gradient. So a standard tool in differential geometry that allows us to distinguish between objects with different volume growths, and this is what essentially we have here, right? On the tree, the volume grows very differently from the grid, is the notion of curvature. So in continuous spaces or manifolds, you can think of curvature as some form of geodesic dispersion. So I take nearby points, I shoot geodesics from them at the same speed and in parallel, and I look what happens to them after a certain time, so whether they will converge. And in this case, I'm looking locally at something that looks like a sphere. If they remain parallel, so we're talking about Euclidean geometry in this case, with zero curvature, right, it's flat. Or if the geodesics diverge, then we look at something that looks like a paraboloid and it has negative curvature, sorry, hyperboloid. And we can apply the same notion to graphs, so we can talk about a discrete analogy of Ricci curvature on the graph, or some form of edge dispersion. So if I start with two nodes connected by an edge and I look at edges that emanate from these nodes, I can examine whether they tend to form triangles. So we are looking at clique-like objects in this case, and we can call them positively curved. If I form rectangles, then I'm looking at something that looks like a grid, and if I don't form any rectangles or triangles, and actually the nodes become more distant, then we are looking at something similar to a tree. And there are standard definitions of discrete curvatures of graphs. So two most popular constructions due to Foreman and Olivier. So here we define our own construction that is a little bit similar to Foreman. We call it balanced Foreman curvature, and essentially it counts certain types of triangles and rectangles. Again, allow me to skip the details. What is important that it reproduces the behavior that we have in the continuous case. So cliques have positive curvature, grids have zero curvature, and trees have negative curvature. And we can also prove some relation to the Olivier curvature, certain bound. We can also say that if the graph is positively curved, then the volume growth is polynomial, like we expect in the continuous case. We can also relate it to the Chigger constant, to the spectral properties of the graph. But I refer to the paper for more details. So this is importantly an age-wise quantity, so we can measure the quantity of every age in the graph. And the main result of the paper is that if I have many edges, if I have a graph with negative edges, negatively curved edges, then there exist many nodes for which this Jacobian that measures our sensitivity is small. So in other words, we have the oversquashing phenomenon, and it is attributed to negatively curved edges. So simply put, negatively curved edges in graphs are the bottlenecks that cause the oversquashing, which is a little bit expected, but yeah, it's good to see it proven formally. And now, once we know this, we can devise a procedure that we call stochastic discrete Ricci flow that surgically removes some of these problematic edges and optionally replaces them by edges with larger curvature. And this is a form of graph rewiring that doesn't change the structure of the graph dramatically, but makes it much friendlier for message passing, as opposed to other techniques relying, for example, on personalized PageRank that do connectivity diffusion and can change the graph dramatically. And we show that this technique allows to improve the performance of graph neural networks, especially in heterophilic settings where we cannot assume anymore that, for example, the labels of two adjacent nodes will be the same. So that's one of the settings where graph neural networks tend to struggle. Now, in the remaining time, let me just mention a couple of more exotic constructions. So far we're talking about processes that happen on the graph, but I said before that graphs are kind of poor in structure. So we can we can invent some additional structure which helps us to obtain more interesting properties. One of such structures is what is called cellular shifts. So cellular shift, very simply put, is a way of attaching vector spaces to every node and every edge of the graph, and then linear maps that connect between them. So think of a graph as an analogy of a manifold, so it's purely topological object where you don't have the notion of distance and direction, you have only a notion of neighborhood, right? Same way as we have on a manifold. So a way of attaching geometry to a manifold is in the form of parallel transport or connection. So on a manifold, you have around every point, you have what is called the tangent space, and a connection is a way that connects two nearby tangent spaces. So it can be defined, it's more general than a metric. You can define it independently of the Riemannian metric, and if you have a metric, you have a special type of connection that is called the Levi-Civita connection. So by analogy, you can think of this cellular shift as a way of endowing the graph with geometry that if we now perform diffusion on this kind of structure, we get more interesting and richer properties that, for example, we can relate to node classification and separation capability. So we can define expressive power of graph neural networks in these terms. And we show that we are able to cope with heterophilic settings and oversmoothing, which are common phenomena that are observed in graph neural networks. So to make things more explicit, so basically we show that we can make a learnable transport map, right? We can define a diffusion equation on the graph. So it's, in this case, it's a linear diffusion. So we can define an analogy of the Laplacian operator, what we call the shift Laplacian. And with respect to this, with this operator, we can run a diffusion on the graph with some initial conditions and look at what happens to the diffusion in the limit, like you see here. So the limit of the diffusion can be thought of as a node classification, and you can always find an appropriate sheaf, right? Some kind of an oracle. It has a lot of degrees of freedom, obviously. So it's a theoretical exercise that will allow to separate the nodes of the graph. And the question is how to choose this sheaf. So what we can do is we can look at certain classes of these sheaves by looking at certain types of restriction maps, right? Of these maps that connect between the spaces. Algebraic topology, these are called stocks. And look at the limit of the diffusion equation. So to make things concrete, here is the typical result that we get. So if we have a family of connected graphs, and we have
Michael, we have that problem again.
Nodes that satisfy certain homophilic settings.
It's black again for some reason.
Can you see me now?
Yeah, I can see you, but the slides are black. Possibly it's like an animation or something.
Is it better?
No, continuous black.
Yeah. Okay. Should I try to stop sharing and share again?
Perhaps, yeah. Yeah, now it's okay.
Apologies for that. Okay, so I stopped sharing. Let me do it again. Okay. Can you see my screen again?
Yes, it's perfect. Thank you.
Thank you. Sorry for that. Yeah, so this is one of the results, right? So here we assume that the setting is homophilic. Basically, nodes that are connected by edges share similar labels, and we show that GCN type architectures, right? So graph convolutional architectures that assumes symmetric scalar transport maps. So we are talking about a trivial case of one-dimensional stocks, one-dimensional sheaf, can separate nodes in this case, right? So we're talking about two classes, so it's binary classification. But if we move away from the homophilic setting, and now we assume heterophily, so we see that under this assumption of symmetry, GCN type architectures are no more powerful enough to achieve this separation. And what we need to assume is asymmetric transport maps. So in particular, we need to be able to have this asymmetry between neighbor nodes that belong to different classes. And this explains recent works that use negatively weighted edges in graphs from the algebraic topological standpoint. Now, we can also relate the dimensionality of the sheaf to a number of classes. And we can also study some additional assumptions on the restriction maps, for example, making them orthogonal. So in case of orthogonality, it also nicely connects to differential geometry. In this case, we can talk about connections on basically an analogy of discrete analogy of connections and a notion of connectional Laplacians that were used by, for example, by Mitzinger in his work on synchronization on graphs. So this is a particular case of our sheaf diffusion. So in the interest of time, let me finish and basically again come back to the original desire. So we wanted, our initial starting point was to revisit learning on graphs as some kind of physical processes which we can parameterize and tune the parameters in an optimal way for the problem that we have at hand. And the system is described by differential equations that we can discretize in many different ways and obtain graph neural networks as the discretizations of these equations. And we don't need to limit ourselves to diffusion equations. So here is another example. This was actually a paper that now has just been accepted to ICML. So that was collaboration with colleagues from Zurich, from ETH, where we considered a system of oscillators at every node of the graph coupled by the graph structure that is learnable. And in this case, we have kinetic higher order terms in the equation. So they have both wave type and diffusion type behavior. And we show that this kind of system allows to avoid certain phenomena such as oversmoothing that you see in traditional graph neural network architectures. So I have, well, this funny picture that is due to Michael Galkin from Mila that shows that well, these are exotic constructions in the that are maybe too exotic in the graph neural network community, but these are interesting new viewpoints that are intimately relating graph neural networks to fields that are less known, such as differential geometry, algebraic topology, differential equations. They allow to study old problems from different perspectives and take a mathematically principled viewpoint on otherwise arbitrary architectural choices, such as, for example, graph rewiring, positional encoding in graph neural networks, also better understanding of phenomena such as oversmoothing and heterophily. And I think it's just a beginning. There are many open and interesting questions that can be addressed by these tools. So I will stop here. Thank you very much for your attention. We'll be very glad to answer any questions.
Thanks a lot, Michael. Very interesting approaches that you are investigating. I have some questions from the audience and some of myself. So perhaps for the sake of a better discussion, perhaps you can just stop sharing and we can have like a chat.
Yeah.
Okay, so the first, these explorations on graph learning, they are a little bit new to me. So suppose that I have a new problem. With your experience, how do you approach a new problem? Like you have different ways of diffusion, right? So what you do normally, you try to understand the structure of the problem to see what's the first modeling of the nodes, and then you try different ways of diffusion, or you have like some way of having the feeling for which, oh, this should be more promising than that. So how do you normally approach a new problem?
So new problem, well, depends what you call a new problem. So if, let's say, the problem is node classification, right? So let's say that your what is new is a data set, right? So you have a graph that comes to you that you have seen before, right? You have node features, you might have some node labels, so you know the labels of some nodes, you want to predict the rest of the nodes, right? So basically what you will be doing, you will be diffusing, so right, so you discretize the diffusion equation. It is implemented as a form of message passing, so I'm exchanging information between my neighbors, right? You can think of it as discretization of some differential operator, or in computer science terminology, it's message passing. Now, what is learnable here are the parameters of this message passing. So what exactly do I do with information that I receive from my neighbors? How I aggregate them to update the node features for the next iteration. So
right.
That's,
so I understand from that point of view that it works great for supervised techniques like node classification, for instance. But what's the state of the art now in terms of graph learning for when you have like very few non-annotated labels, like very few labels, like one-shot learning? How do you approach that with graph solutions and diffusion methods?
So when you have, well, we actually have a recent paper where we show that the amount of labels can be extremely sparse. So you can propagate, basically, well, it requires certain assumptions, typically assumption of homophily, but because, well, also probably some assumptions about the graph, but roughly speaking, in a graph unlike a grid, you have, you see many neighbors, so it is likely that some of your neighbors, or maybe after a few steps of propagation, will contain the information that you're looking for. So we show that, for example, where you have just 1% of annotated nodes, you can achieve very good performance. So it really depends on the problem. It depends on the assumptions about the labels, about the features, about the structure of the graph.
One other curiosity that I have is, for me, it seems that it's very parallelizable. So all the diffusion methods that you apply could be parallelized. So is that the case? So you can like send to several different nodes and it will work okay, or you need some serialization yet?
So it is parallelizable, okay, on paper, right? So here is the big gap, and this is actually a very important point. So in principle, because they have shared function that you apply to every node, yes, it is parallelizable. So every node can be mapped to individual computing unit and processed in parallel. The issue is the following, that it is not necessarily well compatible with standard hardware architectures like GPUs. So GPUs like a stream of data on which you apply the same thing, like convolution, right? So it's seeing the single instruction multiple data type of architectures. Now in graphs, you don't have this sequential access even in memory, because it requires random access. So a node in a social network, for example, one node might have a million neighbors and another one might have just a few, right? We have very popular users, for example. So it is very unbalanced, and as a result, what is typically done, you try to fit your graph in memory. And nowadays GPUs have a lot of memory, so the graph would fit in memory. If it doesn't, then it's a problem. So then you suddenly need to account for the underlying hardware when you do message passing, and if your nodes happen to be in the same part of the memory hierarchy, then the cost of sending a message will be significantly lower, maybe orders of magnitude, than sending message across different computational units or across different levels in the memory hierarchy. Now, why thinking of graph neural networks as differential equations is very healthy from this point of view, because these are standard techniques, these are standard problems that are addressed in scientific computing, right? A huge system of equations that you cannot solve it on a single computer, you need to solve it on a cluster. It is very standard way of decomposing the domain into multiple partially overlapping parts. Then you solve sub-problems on each domain and you try to minimize the communication across these sub-problems. So basically, if you were able to partition your graph in such a way and also change it, so massage the graph in a way that it is friendlier for the underlying architecture by some form of graph rewiring, then suddenly you can make your message passing compatible and friendly also for the hardware architecture. So this is something that is, in general, almost always overlooked in the field.
Okay, thank you. I have some questions here. Thomas is asking if the manifold embedding that you showed use the Nash theorems, the standard way.
So short answer is no. Basically Nash theorem is slightly different. So Nash theorem tells you that any Riemannian metric can be realized by an embedding into a Euclidean space of sufficiently high dimension if the manifold is sufficiently smooth, right? So there are several results, but this is roughly what they're saying. What I was talking about is a problem of isometric embedding. So I have a metric space, a discrete metric space in this case, a graph, where I try to replace the nodes with points on some space, right, on a manifold or maybe a vector in the Euclidean space, such that the distances in that new space represent the distances in the original space. So roughly what I can say that if I know that certain nodes are my neighbors in the graph, I want them to be neighbors in the embedding space. So this is usually almost always impossible. You can find very simple examples where this is impossible.
Another one, this is from Ivan, a postdoc of our lab. Would you expect a characterization of the singularities and resolution through surgeries for the Ricci flow on graphs similar to Perelman results?
Yeah, so good question. I think honest answer, I don't know. So I don't understand Perelman's proof, so I understand very roughly the idea. I'm not sure that the surgery that was used there applies to graph, but yeah, this is an uneducated guess. Maybe there is some connection.
Right. Another from Ivan, would you make sense to try to adapt mean curvature flows for graphs, assuming we can find good embeddings?
Yeah, it's a good question. So mean curvature flows have been used in computer vision for certain curve evolution, right, and then certain types of segmentation problems, for example. So unlike the curvatures that we were considering, it is not intrinsic, so it assumes some realization of the graph in some space, right? So some embedding. It is interesting actually what it does, because basically it mixes positional and feature coordinates, and I don't have a clear intuition what would be the outcome of such a mean curvature flow, but it probably all again boils down to the embedding or the metric that you define. So if you make the metric learnable, then maybe you can say that I have some fixed process like mean curvature flow, and I tune the definition of the metric to make it output something meaningful.
Right.
I haven't tried, so I don't know.
Tomas is asking, FNN's algorithms, they are well suitable for computing balanced metrics based on Donaldson algorithm, and then allowing machine learning methods for approximating non-analytical functions, as for example, color potential. Are GNNs being considered to also do so? How do they compare to FFN?
So what is FNN?
Tomas, could you clarify? I think it's Ford neural networks or something, or flow. Feed-forward networks.
Okay, feed-forward networks. Well suitable for computing balanced metrics based on Donaldson algorithm. No, I don't know how to answer this question. No. Yeah, sorry. Yeah.
Some questions are difficult, and some are not related, but it's not a problem. GGA, also a researcher in our lab, he works with graphs. Thank you for the great presentation. In the line of the first question of myself, how do you approach a problem when the data are not naturally represented as graphs? How to construct the graph, and how these graph construction processes could affect the results? That's a very difficult one.
Yeah, so this is very good question. So, well, let's say that we don't have a graph, right? So assume that what you're given is a set of points, right? So point cloud in some space. So actually, now the common wisdom of machine learning is you can assume that there is a graph, it's a complete graph, whose weights you are learning. So this is how transformers operate. So transformers are a special case of graph neural networks where you allow any pairwise interaction between any pair of nodes, right? And basically you use the attention to somehow learn the structure of this graph. So what has been done actually for many years already now in machine learning, typically in unsupervised settings, is this manifold assumption that you assume that your data, even though it lives in a very high dimensional space, it has some low intrinsic dimensionality. And the metaphor for this is a manifold, right? So it's not strictly speaking in a manifold in the strict sense of differential geometry, but somehow low dimensional space that has very high codimension in the space where your data lives. Now, this historically, the structure of this space has been represented as a graph, usually k-nearest neighbor graph. So you try to capture the structure of this manifold by looking at neighbors, and then typically what you will do, you will try to embed this graph in some low dimensional space. So this is how nonlinear dimensionality reduction of manifold learning works. And it is still used, like TSNE, for example, still used for data visualization. Now, what happens, why these methods actually never really worked, and there are much fancier things also in topological data analysis, where you try to build some higher dimensional, higher order spaces like simplicial complexes. So why this has never worked? First of all, you always need to typically transform your data, basically to extract some features from the data. So you move from the original representation to some other representation, then you construct the graph, then you embed it, and then you apply some machine learning to it. So all these stages are separate. And the way that you perform each of these stages affects what the output will be. So in a sense, you have to work very hard to choose how you build the graph and how you embed it to produce something meaningful. Nowadays, you can put everything into a single pipeline that is end-to-end differentiable. So you can learn the graph, and you can learn some filter on the graph that will be optimal for the task that you are trying to solve. So there are actually graph neural networks where the structure of the graph is latent and is learnable, either in some parametric form. There are many ways of doing it. We also had some papers in that direction. So I don't know if it answers your question, but yeah, that's our architectures.
Okay. Here's one from Alexandre, and I also have this doubt. In the beginning, you mentioned that you gain interpretability with these approaches. Could you elaborate more on the interpretability side of using this kind of graphs?
Yeah, so, well, I should say that interpretability is a very vague concept, and it's probably largely in the eyes of the beholder. So in graph neural networks, obviously, deep learning approaches in general, they're kind of black or gray boxes. So they depend very much on what you do, right? So the architecture itself, as well as the data on which you train. Now, there have been some attempts, for example, trying to bring in causality, so the graph can be interpreted as causal relations in some cases, or try to identify, typically this is in graph classification problems like what is used in chemistry, where you try to predict properties of molecules, try to identify some substructures in the graph that are responsible for certain behavior. Again, in molecules, it's very common. You have some chemical group that gives the molecule certain chemical or physical properties. So that was, for example, the graph explainer from the group of Hughes. Now, I was mentioning a different type of interpretability, and it's interpretability of the graph neural network itself. So what we are trying to do here is we come from certain energy. Maybe it was not explicit in this talk, and well, we maybe didn't explore it too much in the previous papers. We do it now in some subsequent work that is still unpublished. So we start with an energy that looks like Dirichlet energy. We can parameterize it. So we parameterize it through the metric in the feature space, for example. It can also be dependent on the position on the graph. And then we find a gradient flow that minimizes this energy, and we discretize it to form the graph neural network. So we gain here several things. First of all, we have a familiar energy, right? So it measures smoothness with respect to some metric. And it's the metric that you design, that you build, that is most suitable for your problem. So we don't parameterize each layer of the network. We parameterize the problem, the energy, or the gradient flow.
Right.
So I'm not claiming that this is the interpretability, but at least to me, it is much more interpretable than standard black box graph neural networks.
Right. This one from Giuliano. how do you identify that the diffusion has ended? Is there any way to identify the phase transition from a non-clustered graph to the clustered graph?
Yeah, it's a good question. So we typically stop it after some time, and this time is could be also learnable parameter. We can also, well, this was done mainly for theoretical analysis. We allow it to run to infinity. So we look at the limit case of the diffusion, and this is to show the expressive power of the graph neural network. And maybe expressive power is an interesting thing because traditionally in the literature there is this very convenient analogy to the Weisfeiler-Lehman algorithm that message passing under some assumptions is equivalent to Weisfeiler-Lehman algorithm, and then you can say that your graph neural network is as expressive as WL test. Now, this is a completely different approach. It is it's not relying on WL hierarchy. You're looking at basically what kind of limit cases you can reach with your diffusion. And what we show, for example, in neural shift diffusion is that you can choose the structure of the shift in such a way that you can guarantee to classify a certain number of, for example, node types under certain assumptions about homophily or heterophily. So it's very different again from the WL setting, because WL test talks about classification of graphs. Here we're talking about classification of nodes. It usually doesn't allow to incorporate assumptions about the homophily or heterophily, so it considers the graph structure on its own. But it's interesting and fresh viewpoint, in my opinion.
Great.
So again, I don't know if I answered the question. I think
no, it's a great discussion. I have one from Kyle. In certain scenarios, the graph structure is given according to some a priori knowledge. When using graph rewiring techniques and or graph diffusion, how does graph initialization affect the result? Is there any guarantee of convergence?
Yeah, it's a good question. So, well, I don't think that I have a full answer to it, and I think in general this is more or less an open question in the community. So the graph in graph neural networks has a dual role. So it's part of the input, but it's also the computational structure. And the traditional design of graph neural networks, it was to stick to the same input graph. So you take the input graph, you propagate information on the same graph. Now, in modern architectures, this is almost never done exactly in this way. Now, what you can show furthermore is that if you start with your graph and you perturb it in some way, you can actually be provably more expressive. So just by removing a single node, so take your graph, and all these examples that I showed where you cannot distinguish between the graphs by WL test. So if you remove a node or an edge and you look at all the possible subgraphs that are obtained by this kind of removal, right? So instead of a graph, you have a collection of subgraphs. Then by doing message passing or diffusion on these graphs and then aggregating these results, it can be strictly more expressive than WL. Actually, it can be somewhere between 2WL and 3WL in this Weisfeiler-Lehman hierarchy. So it is actually probably beneficial not to use the original graph, but to modify it in a very particular case. Now, how drastic can this modification be is an open question. Right. So there is a class of results in graph theory that are called reconstruction conjectures, which tell you that, for example, by removing every time one node from the graph and looking at all the subgraphs that you obtain in this way, you can recover back the original graph. So basically, you have perfect isomorphism classification. This was proven for graphs with a number of nodes more than 13, I think, by exhaustive search. So it is an open question for general graphs. And there are similar results when you remove multiple nodes. So you can think of graph rewiring in this way. So it is probably beneficial in some cases, but when you make it more dramatic, you don't know. Theoretically.
All right. Very good, Michael. I don't have any other question. I would just like to finish asking you if someone wants to start exploring this area of graph neural networks and diffusion. Is there a particular book that you recommend or a particular reading that's like the starting point?
Yeah, well, there are obviously multiple review papers. So we are now writing a book about geometric deep learning. So it doesn't only cover graphs. So it covers, I would say, most of the deep learning architectures, probably all the popular deep learning architectures, maybe with the exception of reinforcement learning, from the same principles of symmetry and invariance. So we like, maybe slightly arrogantly, to call it the Erlangen program of machine learning. So this will hopefully appear sometimes next year with MIT Press. So we'll put it online in a preprint. Currently, it's just a long paper, about 150 pages that we published last year. We have an entire course that we recorded last year as well, based on the book. Specifically for graphs, there are several recent review papers. I think the most recent one about theoretical results by Stephanie Jägelka.
Very good. One last question from Ahmed Ismin. Thank you for joining us, Ahmed. Thank you for the great talk. Do you have some work on cause effect to provide some interpretability using graph diffusion?
So not with graph diffusion. I'm not an expert in causal inference. I think it's interesting, and especially where it's interesting is in different biological problems, where you try, for example, to identify mechanism of disease and therapy. There are some interesting results in this direction from, well, multiple groups. What we have is a theoretical paper that, in the context of reinforcement learning, that looks at the following problem. When you have a universe where you have different environments, and they are modeled as graphs. So you assume that we have some shared environment, some shared causal graph, but there are also different components for every environment. And we show sample efficiency in generalization in this kind of setting. So roughly you can think of, let's say you have a robot that navigates in a different room, where every time the room is different, but the laws of physics in this room will always be the same. So that's roughly the idea. So in biological terms, you can see that you have different cell lines that are associated with different phenotypes or different diseases, but somehow the overall principles of cell biology and the mechanics are more or less the same, right? So you have some shared causal component, but some individual tweaking that depend on the particular type of cells, something of this kind.
Thanks a lot, Michael. It was very good to have you here today to discuss with us. Soon we will post this on YouTube for others that didn't have the time to join. We've got like about 200 people that registered, so it's a very good number. Thanks a lot and take care.
Thank you. Have a good day.
For everyone else, thank you for joining as well. We are going to meet again in about 2 weeks for Melanie Mitchell's talk. So stay tuned. If you need anything, just let us know. Thank you. Bye-bye.